Today, we're going to take a bit of a step back from the multi-agent problem and look more into the techniques needed to do just general reinforcement learning with approximation. And the term here, deep reinforcement learning, just means that sometimes the approximation function we use is going to be a neural network function. Like, how deep the network is kind of depends on the problem. This is just sort of a generic term, implying that like this could be used to solve very complex problems if the network is big enough and has enough, parameters to actually generalize across a very large state space. But really, this the context of doing reinforcement learning with approximation does not really depend on the specific function approximator we're using. Like a lot of the focus now is on deep neural networks because they've been very successful in certain tasks. But really, a lot of the math and the techniques we build up just requires some function that we can take a gradient of. And a very simple subset of those functions are just linear functions, which is always what you start with when you build up these approximation techniques, because the gradients of linear functions is really basic. But the first thing we actually try to use function approximation for is previously we had looked at value function approaches to solve problems. So this is where you try to collect estimates for these are state action values. So in every state we have some value estimate for a particular action. And the reason why we do this is because in tabular reinforcement learning, there is some exact function of this where if we have it, then we can just follow the optimal policy directly, or like we can use this like with value iteration. We compute these exact value functions for the optimal policy, and then from that we can just follow the optimal policy. But if we don't have the ability to just get these exact values, you can also estimate these values by collecting samples. But in that case, you still have a distinct table of values, and you're just collecting a bunch of data from interacting with the environment and sort of averaging values. And you're still doing the same thing you do when you have the exact values. It's just that they're not exact yet, and as the algorithm runs, they eventually converge. But now we're going to be looking at a situation where we try to write down a function that just produces a value estimate for the state action values. But it's not going to be a distinct value stored in a table. It's going to be something that, some function, like somehow we have to transform the state action pair into something that the function can take as an input and then produce this output value. And then this is just showing like when you do Q learning with like tabular values, this is the update that you try to do as you go through the environment, right? But in this case, this is where we have like a distinct value for this, and we want to just update it with new data that we collect. And this A is some learning rate. Now, obviously, we can't do this kind of update when we have function approximation, because like we don't, this isn't the way the function works. It doesn't just have a value that we can update. Instead, it has parameters, and those parameters control how the function behaves across the inputs. We have to have a way of updating the parameters. And it's sort of well, they mention it here, but we basically define this loss function. And once we have the loss function, we can then compute a gradient to update the parameters. But like really, what is this loss function? Well, the loss function is our attempt to use these target values and say that we want our state action value function to better approximate the true values. Now, in this case, we don't actually have the true values. So usually what we do, which is being shown here, is that we estimate the target value with the value function itself. This is also what we do in the tabular problem. We don't have to do this. We could do like a Monte Carlo method, which they actually don't mention here, but like you can do this reinforcement learning with approximation where we don't like this is what we do in like TD learning, where we have the reward for some immediate transition that we've had, but then we have to use our existing value function to fill in all of the future values because, right, we need to know like what is the true value in this state. We can't just use the immediate reward unless the next state is terminal, in which case all that matters is the next reward. So, here, when we do n-step learning, we take a bunch of these R's like t, t+1, t+2, etc. And at some endpoint, we pick, at some future state, we then replace it with this value. So, importantly, when we write down this loss function, there's this idea, like when you do, supervised learning, where you have your function that you're trying to match with some data set, or like y, let's say y comes from this data set. In this case, there is no data set. We're just going to be, generating these target values as the learning process goes on. But let's imagine, we had some data set. And when we have the loss function, we don't, like we're trying to calculate the gradient with respect to the parameters data, right? And the target values don't depend on the parameters. They're just there and they provide the target for the function. But like the function, the whole point of this loss is to update the parameters to better match the target values. And if the target values, like in this case, actually are generated using the function itself, then actually these target values also depend on theta. But when we actually do this loss function and compute the gradient, we assume the target values don't depend on theta. And that's why these methods, if you look at the Sutton and Barto book, here we go, is this the... Yeah, so like the Sutton and Barto book refers to these methods like this sort of Q-learning style function with approximation as semi-gradient methods. Because if we were computing the true gradient of this, we would have to also take the gradient with respect to the target values, but we don't want to do that. We want to treat the target values as just a constant. So, yeah, this is just in the Sutton and Barto book, how they write down. This is in the case of doing a value function, not a state action value function. But here, this is supposed to be whatever the true value function is, right? Like here, we're training the parameters to try to match our approximation as closely as possible to the true value function. And this, if it really is the true value function, these are just exact values. They also don't depend on the parameters. But as soon as we introduce this other, this type of estimate or bootstrap estimate, then it becomes a semi-gradient method, like is being shown here. Now, also, we can do gradient Monte Carlo with the same style of learning, where now our target value is something that we've sampled all the way to the end of an episode. This only works in environments where the episode has like a finite length. It doesn't work for continuing problems where an episode doesn't end, there is no terminal state. And this actually restores the property where the estimate doesn't depend on the parameters. But when we have a semi-gradient method, there's all kinds of problems that arise from this. I mean, there's actually a different problem which isn't even mentioned in the multi-agent book, which is that it's sort of, this is a very simple example from the Sutton and Barto book where we have a true value function, which is this line, right, this red line. And then this is our approximation function, right? Not a neural network, but a different style of approximation. But the nature of the approximation function, all the values for states that are close together share the same value, right? So you could see like this value function, if once it's converged, is trying to match the true value function as close as possible. With this caveat, it actually depends on the state distribution as well. Another thing. So basically, it places more importance in the error function on states that are more frequently visited, which is also, it makes sense if you're in a reinforcement learning problem. You want to make sure your function is working best at the states that you visit the most frequently. This is just usually how the problem is set up. But if we use a semi-gradient method, which I believe there's a table of this somewhere, I think I go past it here. So now you can't see it on the same plot, but this is showing what it converges to with a semi-gradient method. And it actually is a different value function. It doesn't actually minimize the error with the true value function. And this is just something inevitable whenever you do bootstrap estimation. You can't fix this. All you can do is hope that this deviation, like here you could see these values are now, especially at the edges, are very far off from the true value function compared to, the Monte Carlo method. And you just hope that this deviation doesn't ruin your ability to find optimal behavior. But, the MARL book really only, at least for these type of methods, only talks about sort of the TD style learning, where we use an estimate, a bootstrap estimate like this. Now, I had previously discussed this whole, like, kind of a big overview of approximation methods in one of these previous sessions. Sorry, this is the playlist for people of the meetings where we cover just regular reinforcement learning. So if you go down here towards the end, I did sort of a session on 2 sessions that just covered approximation methods overall. So both linear and then nonlinear value functions. So that's like probably, if you look at these two, it's probably a more thorough overview than what you get in this chapter, which kind of just, it very quickly gets to more advanced versions of the algorithms. Also, I mean, it's also covered basically anything after chapter 9 in the Sutton and Barto book, and these sessions cover all of the approximation techniques. And also, chapter 11 in particular covers problems that can occur with approximation and things where things diverge, and that's also discussed briefly in the multi-agent book. But in one of these videos, I had sort of this prepared, these notes that do kind of an overview of how the approximation methods work and sort of the general characteristics of them. But we can sort of quickly go over it again here. Something which isn't really mentioned too much in the MARL book also is the fact that, see, they write these value functions out like this is some function, right, that takes the state action pair and it's based on these parameters and it produces some value here. Now, practically, when we create these functions, usually we want a function where we give it a state and then our environment has some set of actions that exist in it. And ideally, we would like to output just all of the action values at once, because we actually, for these algorithms, need to take the maximization over it anyway. Like we need to know which action is the one that we're selecting and also what the value is for that action. See, like here, we also have to do the argmax here of this function. So there's some of the complexity hidden in the way this is written. I think they have an example here of, yeah, so here, like they have an example, little diagram of like, if you were going to write down a neural network to do this, they actually write it where you take the state and then the network just has one output for every action so that we can just compare all the action values together. Now, of course, this is implying that the state is something we can feed into the neural network, but really, like, your state could be some abstract collection of things and data structures. Like, you have to turn it into usually just some kind of vector, and you don't really want the values here in the vector to be just unrestricted arbitrary values, because neural networks do a pretty bad job when the input vector can just the values could exist over an arbitrarily large range. So usually we actually do have to transform the state into some kind of feature vector. Now, this transformation is much more important when we do linear approximation, because if you look here, when we do linear approximation, let's say, and we're trying to estimate the state values, we'll have some vector of parameters of length n. And then when we do the output, when we do also state action value, or whether we're just learning a single value or we're learning the state action values, we're going to do either a dot product or a matrix multiplication of the parameters with the feature vector for that state S. Now, this is designed so that the feature vector has to match the dimensions of the parameter vector. So let's say, like, if we map our state to a feature vector of length 10, then our parameter vector or our parameter matrix is going to need one of the dimensions is going to have to match that of size 10. Now, for linear approximation, we just have this single operation of matrix multiplication or a dot product. So it becomes really important how we transform the state into a feature vector. Like if you look back at the Sutton and Barto book and this example here, this is effectively a feature vector called like a state aggregation feature vector, where we just take a state and we map that state to some index, where here, like, these plateaus indicate the number of parameters that we have. So let's say we have like 10 parameters here for this type of approximation, and each parameter just dictates the value for the states that are in this band of the state space. Now, this is the simplest type of like linear approximation that you can do, where you just bucket the states into different sections. You can also do actually this chapter in the Sutton and Barto book, because it deals primarily with linear approximation, talks a lot about different styles of feature vectors you can make, different like Fourier features, different types of coarse coding and tile coding. But these types of feature vectors are nice. And you can even feed these into neural networks as well. Like you can take your state space, turn it into a feature vector like this. And then, if the linear approximation isn't good enough, you can still, pass it into a neural network that's more complex. But these are nice because they are binary feature vectors, which can simplify the calculation a lot, right? The values are basically just either 1 or 0. Yeah, Frankie, you have a question?
Yeah, for that semi-gradient method that you mentioned and how the value function, you don't quite get, where the true value function is. Can you explain why that's the case?
So that is it's pretty complicated to understand why. So basically, the issue is that when you do a semi-gradient method, you actually converge to something. Actually, let me see if it's mentioned here. Here. You converge to something called the TD fixed point. Here. So yeah, and actually, if you look at chapter 9 in the Sutton and Barto book, or you look at the videos where we had covered chapter 9, I go into a lot of detail with this, but there's actually, this is only the proof in the linear case. So you can show for linear approximation, like you can actually prove it, that where like the semi-gradient method actually converges to this fixed point value, because the target value also depends on the parameters. So in order for the step update to actually produce no change, it has to be a point in the parameter space where the target value doesn't change and the output value doesn't change, right? So when we do the semi-gradient update, right, we're updating the parameters with this. But in the semi-gradient case, remember, this target value is also based on the function, and it's going to also change. So it's not simply enough that we find a convergence point where this error is minimized, like the difference between the target and the true value. It actually has to be a place where the target value itself also doesn't change after the parameter update. And that's why it's called a fixed point, because it's something where this whole operation where everything is updating produces no change. There is another explanation of it, I believe, in chapter 11. Yeah, I mean, actually, like the coverage of this in the Sutton and Barto book is pretty good, and it is a pretty rich topic. There's this whole discussion of value function geometry here. Sorry, this is like really getting into the weeds of this, which is covered in detail in one of these in these like chapter 11 videos you see here that cover like off policy divergence and value function geometry. But you can actually see when if you set up a really simple problem, there are all these different points you could converge to depending on what type of gradient update you're doing. And yeah, the TD fix point, which, sorry if I'm trying to
Well,
find
let me
it.
see. So, can I ask a question then? Does it
Yeah, sure.
matter? Does it matter on, suppose you do have an update step. So if you update step smaller, does that actually make it converge better or not?
It doesn't matter. It'll still converge to the same point.
Okay.
And so the TD fix point technically is where the projected Bellman error is 0. And you can understand how this all works with value function geometry. But yeah, sorry, it's actually a lot more of a subtle problem than it might seem. And really, like, to prove the convergence to the TD fix point, you really only can do it, I believe, in the linear case. Um, when you combine, and actually, all of the problems that exist with where things don't converge properly also occur in the linear case. Um, so like usually when we have issues where we don't have guaranteed convergence, that usually happens when we do machine learning, with nonlinear functions, because now we have like pseudo convex functions, or like the loss function is pseudo convex. In reinforcement learning, actually, there's other problems with convergence that occur just with linear functions. And when you also introduce nonlinear functions on top of it, you can sometimes just lose all guarantees of convergence. Like, yeah, the TD, I don't even know if the TD fix point is completely valid in the nonlinear case. It
So your sense is that if I introduce nonlinearities, that the convergence becomes harder. But why is that the case, or why do you feel that way? Sorry.
Well, I mean, even in supervised learning, using a nonlinear function can make convergence harder, right? Just because you don't have this convexity guarantee, which you have with linear functions. So if you're just doing
Right.
supervised learning with linear functions, you have great guarantees of convergence. You don't have to worry about it. Once you introduce nonlinear training, you need to start playing around with a bunch of hyperparameters. See, you can have training runs where the gradient descent just gets stuck somewhere. It doesn't, you have a lot of inconsistency. But I'm saying with reinforcement learning, you even have problems with linear function approximation, like some of
Uh,
these
but uh,
problems,
but then my
which have
question is,
nothing to do with the fact that it's nonlinear. Something like you don't even need to introduce nonlinear function approximation to run into problems.
uh, sorry, just want to make sure I understand your point. So yes, you might have troubles converging, but my question is more like, is there a proof saying that, in the linear case, you say that, you be kind of away by the TD fixed point. Is there something similar in the non-linear case, or the nonlinear case allows you to actually converge to the correct point?
So in with any kind of semi-gradient method, the only thing that you will converge to, if it does converge, is the TD fixed point, which has, in the linear case, there actually is a guarantee that it is close to the ideal, the value function that minimizes the value error, which is the one that we usually want. However, this bound of how close the TD fixed point is actually not a very tight bound. In fact, gamma usually, like in the book, there's a lot of examples where the gamma is like 0.99, So if this is, as the gamma approaches 1, which often when we solve problems, we do pick a gamma that is fairly close to 1, this is not guaranteed to be very close. Now, this is just like the worst case scenario, right? We saw in this example, in the book, in this very simple example, that the TD fixed point actually is somewhat close to the true value. Right? Here's the true value function, and then the TD fixed point we saw like here, where it's just a little off. So it's more that you have to try and see. You can always use a Monte Carlo method to avoid this problem completely, right? Because a Monte Carlo method does not use a bootstrap estimate. Now, in the nonlinear case, I don't know if there's a guarantee of it converging to the TD fixed point, but that's sort of the best you could hope to do if you're using bootstrapping, is to converge to the TD fixed point.
Thanks.
Yeah, like that. Sorry, there's like there were several sessions that cover these topics. It's not really mentioned that much here. Like there's not even a mention of the TD fixed point here because the focus here is just to introduce the algorithms. But the point is, even this first algorithm we look at has a number of problems that can occur. And actually, this sort of deep Q-learning algorithm in the Sutton and Barto book, they don't even start with this algorithm because it's actually, this is technically an off-policy algorithm, which can be fine when we look at tabular problems. But in the case of approximation, which they mentioned, there is this deadly triad problem, which I'll mention in a little bit. It goes into these problems. The actual first one of these algorithms that you look at for the control problem is actually in chapter 10 here, and it's just this semi-gradient sarsa, actually, rather than Q-learning. If you compare these two algorithms, really the only difference here is that for sarsa, the target function, right here, you see this r plus gamma times q. So that's the part here where we update the target value. So we use the reward and then this function of the next state. When we do a Q-learning style algorithm, we take the maximum of all the action values at the next state. When we do a sarsa algorithm, we are following a policy which is epsilon greedy, which means that unlike this, sometimes we take the maximum action value, sometimes we take a random value. This allows the algorithm to explore enough to guarantee convergence. And in fact, we are following here, right, with probability epsilon, choose a random action. So here we are, in this algorithm, following the same policy that we follow when we do semi-gradient sarsa, where we're following the epsilon greedy policy. However, here our target value is actually a sample of the value function from the policy because we're actually using the Q value at the action we select. Now, if this action selection is the greedy action, it's the same as Q-learning. But this also will use the random action if we select a random action, right, when we select the epsilon greedy policy. This fact that we sometimes use the action value that's not optimal is what makes this an on-policy algorithm. And it avoids problems that come up later when you try to do this off-policy learning, like is shown here. But actually, the details of why this off-policy learning is a problem isn't covered in this book either. All of that is actually covered in chapter 11 of the Sutton and Barto book as well. they do mention in here, they mention a few problems with doing approximation in Q-learning. And actually, we can start going over that. But the basic skeleton of this, it looks a lot just like normal Q-learning. But the difference is that with normal Q-learning, we take this target value and we just use it as a sample, and then we update our value, our action value here, there's no theta, by moving it closer to the target value. Here, we have the target value. We compute a loss function with respect to the target value. I mean, yeah, our loss function includes the target value, and it's a function of the parameters. And then we compute a gradient of this loss, and we update the parameters rather than updating the specific tabular values. Also, this loss function, the way they've written it here, if you actually do this where you just compute the gradient of the loss, notice how in the Sutton and Barto book, they actually say, here it's written where you compute, like they're assuming we're using squared error loss here. That was assumed earlier, sorry, in chapter 9, where this whole parameter update step is based on trying to minimize the value error, which is the squared error difference between the true value function and the approximation function. Now here, this is actually the parameter update, right? Like it's fully done here. Here, this is the gradient of the output here, sorry, of the approximation function at the state action pair with respect to the parameters, right? This is not written as a gradient as a loss function. And actually, it's important to not take the gradient of the loss with later algorithms in this book, because this book also talks about eligibility traces, which is a technique to sort of incorporate multi-step learning very efficiently with approximation. And when you do that technique, you actually have to accumulate these gradients, right? So here we have like the gradient of the value function itself. Here, it's saying update the, I mean, they don't even mention the gradient here, but they say update the parameters by minimizing the loss, right? Here, the loss function involves, the squared error of the target value to this. So this update is derived, but we actually leave this gradient. And this is also not a typical gradient you would see in supervised learning, right? Where you just have, if this Q function is set up like this diagram here, where we have a different update for all the actions. This is saying, compute the gradient of this function output at this state and this particular action, right? If the function is outputting all the action values at once, we have to actually compute a gradient with respect to an output index, like the actual output value itself, not a loss function computed on this. But even the way this is written out, if we compute the gradient of the loss, this is not the typical squared error loss we would have in supervised learning, right? Normally in supervised learning, we have a function that has a certain number of outputs. Like let's say it has 5 outputs, there's 5 actions. Then we would have a data set where the data set would also have 5 outputs. And we'd have a gradient across that data set, some batch of that data set where we're trying to match the outputs, all of the outputs of our function with all of the outputs in the data set. Here, the target value is a single value because it is the target value computed, right, using like here we're taking the max over the action values, right? Like this target value is supposed to represent the true action value for the action that was selected here, right? But here, this output function has all of the action outputs. So we actually need to have a loss function that computes the gradient of the squared error loss at a specific output value. Like we would need to pass into, like as a data set, right? We have a collection of values that we're matching. these target values, but we also have the indices here that we're matching, like the action indices that we have to match, right? Because for every example, we're doing this like for a particular example, we need to know which of these values are we trying to match to the target, right? We're not just matching all of them. Now, you can sort of hack around this by computing the target with like this for this single output value, right? And then if you want to make sure that the loss doesn't accumulate extra losses that you wouldn't normally have, you just have to make sure that all the other outputs, like if this, like let's say we're trying to do the target update based on the first action. So we have a delta with the target value for A1 that we want to actually use as the loss function. Right here, Y, like let's say A here is actually like the first action, right? If this is a typical loss we'd have in like supervised learning, our loss function is going to actually look at all the outputs, and the targets need to include all the outputs too. And then we'd have to make sure that the other corresponding target values here just matched these values, right? So we would actually like go through and fill in the values, do like a forward pass with the network and fill in all the values and then just change one of them for like our, target, our delta target value. But again, that's like not a typical thing you do. It's also like inefficient because then you're doing an extra forward pass to fill in the values. Ideally, we can just tell our, whatever we're using to compute the gradients, that, well, we want this loss function, but, even though our network has like 10 outputs, we want to also pass an index for every target value to tell you, no, only look at the gradient with respect to the loss of this one output value. All the contributions from these other things should be 0. So again, it's just another like kind of wrinkle that's not mentioned here. I mean, also like the feature vector thing is not mentioned here, but typically the states, like here they just show it where the state is just like, fed in. But typically we'd have to map this state somehow to a feature vector. It could be as simple as just taking the values and throwing them in, but usually we want to normalize the values somehow, and we may want to concatenate them in different ways. Just like usually there is a lot that goes into how you actually pass the state information in. It's not, as simple as just dumping the state values into a neural network. So anyway, I'll stop for a second, but does anyone have any question about what we've talked about so far? Mm-hmm. Yes.
Can you go back to your where explicitly you have a gradient of Q formulation?
You mean in the book here?
Right. So in this here, the R plus gamma Q prime, that is kind of where you have the weight update, right? So that part is not for specific, is also for specific action, correct? So you choose a
Yeah, here we're using this is the target value. And with Q learning, the target value is R plus the discount rate times, we look at the subsequent state, but
right.
we take the max because like this is basically like the Bellman update for the optimal value function, where this should match the max value. This is like what we do. This is like literally the update you do in Q learning without a gradient. But here, right, we're just using that target, in the loss function.
Well,
But
so that other one, the A prime, you have to choose A prime, right? Or not here.
Yeah, here you have to know A prime ahead of time. So luckily, so we take the transition, we observe R and S prime.
Yep.
And now since we have S prime, we can just go ahead and pre-choose A prime. We'll actually use A prime later on the next step as well. We just choose it a little early because then we need to use it for the parameter update.
Okay. And then in this case, if you want to map it back to your picture of the neural network one, although, in this case, we're looking at all A's, correct? Then the update on the gradient one. not the deep Q learning, for the gradient update one, we're
This, I mean,
updating.
so
Yeah.
when we do the gradient here, this also is going to be the gradient for just a single A output value. Here, this is the A that we chose in state S,
Yeah.
and this is the A we choose in state S prime.
Okay.
But like for this, but keep in mind, like even though here we only need this one value for the target, we actually had to compute all of them anyway. Because in order to choose A
Choose,
prime,
correct. Yes.
we had to know what they all were. Which is why normally when you write this down, like even for linear approximation, like imagine like if it's linear, this is just a matrix multiplication here. It's not hidden layers. You still would just output all the action values.
Right. And choose a maximum
Yeah. Now
action, for example.
you don't have
Or
to do it this way. Like you can instead map the state action pair itself to a feature vector. And then if you want to compute multiple action values, you would have to basically create a new input and do another, like then your network would only output one value. And actually, if you do that, all these loss gradients and stuff become straightforward because then this is just a single output and this is a single output, right? That would be like, instead here, imagine this is like SA, like you somehow turn SA into the input
state.
vector.
Yeah.
And then you output just one value, right? But, and actually like the Sutton and Barto book does do it that way because it makes all the gradients like this gradient also, usually it would be nice if this was just, right, a single, like our function just took this as a single input. Rather, the truth is most of the time it's Q hat S W, and then we actually need to tell the gradient, well, we only want the gradient with respect to this single output. But again, you don't have to deal with that problem if your function takes SA itself as I mean, the way this is actually written here and here is that the function takes the state action pair as an input.
So in some sense, maybe I'm getting confused here because the line here for W update, it is similar to the W update that you have in the book, right? Because the gradient of Q is kind of the gradient of the loss, of the square loss, correct? So
yeah, no, it is the same. Like this,
yes,
this update step is derived. It's just that, yeah, like yes, like you could write this with the loss function. It's
yeah,
just that they've partially computed it already, and the only term left. So like this contribution here is from like using the chain rule is the
right.
contribution from like the loss function, and then you're left with the gradient term of Q
Got it. Yeah, I just
inside.
wanted to make sure that these two
Yeah.
formulations are actually similar. It's the same,
Oh yeah, yeah,
actually.
yeah.
Yeah,
No,
okay, fine.
like
Yeah,
this is the same exact thing. This just isn't Q learning, but the difference there is this part that
yeah,
it's not a max. Yeah.
yes. Yeah,
So then if you have a linear approximation, which I talked about,
yeah, which is W,
sorry,
yeah,
in this
WQ.
notebook, then yeah, with linear approximation, the gradient's very simple, and it just, sorry, here. So here I show the gradient when we just have
Right.
linear approximation, which is just the feature vector.
Yep.
Right. In this case, with state approximation, it is just the feature vector. In this case, here, this isn't gone over in the Sutton and Barto book, but this is just showing the case of if your Q function is in fact, it doesn't take the state action pair as an input, it takes a state as an input, then you need to do the gradient this way, where it is the feature vector, but only for one of the columns, and then all the other columns are zeroed out.
Yep.
And this is the same kind of gradient you need to do with nonlinear approximation. It's just that this only applies to the final layer.
Mm-hmm.
And then you need to zero out these other gradient terms, and then, it filters backwards. And in general, the terms won't be zero going back through the other layers. But for the final layer, this part of the gradient needs to be zeroed out.
I think you mentioned that the sarsa one was kind of using epsilon policy,
They
epsilon
both
gradient
do.
policy. They both do. Okay, fine.
Yeah.
Okay.
Yeah, both use the epsilon greedy policy. The difference in sarsa is that we actually use the target values that come from the epsilon greedy policy.
Got it.
In Q learning, we don't. So basically, let's say in Q you're doing Q learning and you choose an action and it happens to be the action choice that is random. It's not the the argmax, right? Then our loss update, our bootstrap target, is going to use a target value based on, well, when we're in this state S prime, we're going to take the maximizing action, right? But some of the time when you're actually following the policy, you don't follow the maximizing action. So it just means that this is an off-policy method, which is also true of tabular Q learning. In tabular Q learning, it doesn't actually cause any kind of problem. But we'll see that with approximation, doing this combination of things can sometimes cause the weights, the parameters, sorry, to not converge. But
So,
it's not the only problem.
so I'm a bit confused here because line 5, you choose a random action A prime, right? But
With
then
probability epsilon.
epsilon, correct. But then but the update happens on line 11, right?
Mm-hmm.
Which takes a argmax or A prime, but max, right? So the max A. So 5 you choose with epsilon greedy right here and A prime. But how
Mm-hmm.
can this work for an off policy? Because you might not have that particular action, correct? Or any information about that action, A prime, right? On line 5.
So this is a parameterized function. So basically, whatever input we put into it, it will give us some output.
Okay.
Um,
Okay. Yeah,
yeah,
makes sense now.
it
Thank you.
is true that we may never have visited this before
Yeah.
and trained on it, in which case the value will just be some random value.
Yeah.
But
Makes
actually,
sense.
that problem you're pointing out occurs even if we have visited it, because I'm going to get to the main reason why you have problems with approximation is because when you do tabular methods, so let me see. Sorry, I thought I had like mentioned it clearly here. So when we do approximation methods, because we're mapping the states to some feature vector and then we have parameters, we don't have independence between the states. And you could see it very clearly in this simple example we had from the book. Where was it? Like, right, this example where we had this true value function and then depending on how we do this is just one example of approximation. And here you can clearly see how the state values are related, right? Like if I get a sample point from this state and I do a gradient update, I am effectively changing the value of every state in this band of the state space, right? Like this is just, but even if you have a really abstract space, abstract function, like a neural network, this same principle applies, even though like it might not be just this simple band of states. In fact, you can have global changes, right? Like if this is state aggregation actually does a pretty good job of isolating the states, because even though I change all these states, I don't affect these at all, right? If you do something like, let me show another example here. Like this is an example of doing another kind of linear approximation with fewer parameters, but you know, this approximation function, if you tweak the parameters, it could affect the value of every state, right? Like to some extent. That's also true in general of like of neural networks. You have some function, some output. Any parameter you change could affect all of the state values. And that's the main problem that breaks the assumptions we usually have in reinforcement learning, where we're just trying to collect data from a single state, get a better estimate for that state, and then move on. And over time, hopefully, we accumulate enough data that we have an accurate function. Here, because our approximation function is using parameters, we may collect a bunch of data on one state, update it, you know, but then it could screw up our accuracy of the other states. And that's one of the first things mentioned here as a problem with this deep Q learning. So there's this moving target problem. Now, this is a problem they mention here that if we're going through the environment and we're in some part of the state space, you can like see it here. Like if our neural network is in some part of the state space, let's say we spend a lot of time here, right? And we end up getting a really good value for this part of the state space. But we're using a type of approximation, like in this case, neural networks, that they don't have this nice property like we have in state aggregation. We're only going to affect this. No, we could affect the state, like the function globally. So it may overfit to the states we visited recently and then screw up its knowledge of all these other states. Now, usually when we do supervised learning, we try to sprinkle in representative examples across the problem we care about so that the network is always being reminded of, the general values it's trying to achieve, right? We don't just feed a bunch of batches in that are, from a very narrow part of the state space. Or sorry, like of the data set, right? Like we want to mix up the examples thoroughly. That doesn't naturally happen when we do reinforcement learning, especially when we do this Q learning thing where we might end up spending a lot of time around the same states. Of course, this type of problem here, where we overfit to the states we're visiting currently, right? This is only true with certain types of approximation, right? This is only true when we have this like global dependency of the function output on the parameters. There's a reference here to the Sutton and Barto book about the deadly triad, but this is a different problem, or at least this can also happen with linear approximation, right? And you can create linear approximation that doesn't have this like catastrophic forgetting problem where we optimize, one part of the state space and we forget about the others. However, the deadly triad problem is something that happens when you combine bootstrap targets, function approximation, and off-policy learning, which happens to be the case here. So this also happens with linear function approximation. And the deadly triad can cause a problem where the weights actually diverge, right? It's not the same as like having poor convergence or, the catastrophic forgetting problem, but this is actually potentially a problem where the weights just completely diverge. This even happens with very simple linear problems. There is an example, a famous example in the Sutton and Barto book. Let's see, this Bard's counterexample. Yeah, and actually, I don't know, do I have a diagram of it here? I guess not. In the Sutton and Barto book, you can just see that it doesn't actually matter how complicated the problem is. This deadly triad problem can occur even with very simple problems. And one of them is shown here. Right? This is an example. Here, I mean, this is a contrived function approximation, right? Like this is set up where one of the states has a value of W and the other state has a value of 2W. But, this is just a toy example that like you could have even in a neural network, an example where one of the state values is linked to some collection of parameters and the other is linked to like those same parameters, but with a higher value, with a higher constant multiple. And even with an example as simple as this, the problem you get is that, I mean, you have to do off-policy learning as well. But basically, when you do off-policy learning, it's possible that you never actually end up visiting the state enough that you transfer into. I mean, this is one that ends up showing the problem. Like the problem occurs very quickly. But you can have parts of your state space where you have some version of this with off-policy learning that ends up screwing up the convergence, which is why in the Sutton and Barto book, they talk about these like semi-gradient sarsa algorithm, right, rather than the Q-learning version of it, which is shown in the multi-agent book. Because, right, all you have to do is change your target a little bit. It doesn't actually affect the problem that much, right? You can also converge your epsilon to 0 over time, which also is not a problem. There's nothing wrong with that for sarsa. And then you actually eliminate this deadly triad problem. You still have the problem, the moving target problem, and potentially overfitting to certain states. Yeah, but so this is covered much more thoroughly in the Sutton and Barto book, and there's a number of videos of past meetings where we go into this in more detail and those counter examples. So they do mention here one way you can avoid this problem somewhat, although this is also something borrowed a little bit from double Q-learning, where Q-learning also has a tendency to overestimate action values because there's of these argmaxes and maximization operators and the thing. Another approach is to have two networks, a target network and a value network. And what you can do is you can have a target network that you keep kind of close to the value network, but maybe you don't update it very often. So there's long periods of time where its values haven't updated and are not like overfitting in the same way to the recent data. And then even if you're in a part of the state space where you're accumulating a lot of recent data, your target value still has the benefit of using an older network that hasn't necessarily overfit. So you don't have this overfitting problem in every aspect of your estimate, right? Like you still have it that you're computing this gradient here, but now the target value, you're now using a different network for the target value, right? And then on some interval, you would make them match. There's sort of something that looks similar to this in even double Q learning, but that's a little bit different. That actually involves when you do this max operator, you do the max operator from one set of estimates. So like you use one function to figure out what is the maximizing action, but then you actually feed that action into a second network, which is being trained differently. And that is the value itself. So you don't have this double maximization problem where you're actually, one network is both being used to figure out what the maximum value is and the value itself, right? That eliminates the problem in a lot of cases where if a network value isn't exactly accurate, then if you use one, like if it's not really confident that this is the maximizing value, then you'll pick what appears to be maximizing value from one network, you'll feed it into the other one, it'll just be an ordinary value because they don't actually match. Like they don't agree on what is the maximizing action. So it helps just make it so the only time you're going to be getting like a true max value is when both networks agree on it. But that's more what you do in like, what's being described here isn't exactly what you do in true like, double Q learning or double sarsa. But this is just addressing this target problem where we don't want the target values to be too correlated with the updates that we've recently had for the network. Does that make some sense to people? The idea that we could use a separate network just for the target values, but not actually for the, like the loss function is still going to be based on the value network. The other issue with the overfitting is that, if we're visiting one part of the state space a lot, right, we have this problem, like I said, where we could over-optimize for just the recent examples. And there's an idea about, breaking these correlations where we ideally, like when we do supervised learning, we want to create batches of data that are representative of the data set, right? They're spread out. their distribution of inputs sort of matches the overall distribution in the input set. Usually we do that by just randomly sampling batches from our data. And that's sort of what you can do here, if it's mentioned. But the idea is to create something called a replay buffer, where as we go through the problem, we just collect data and we just accumulate examples that we've seen, examples of transitions. I'll just skip ahead a little bit. It's shown here. But when we say like a transition, we're talking about the state action pair, the reward, and the subsequent state. This is all the information we need to calculate sort of the target value we might need later. So we basically just build a data set over time as we go through the problem. And then we sample a batch from this data set and then do the gradient update on the entire batch over time. So the most recent data we've collected might not even be in the batch, right? We're just using the current network, right? This part is the same, where we use the current network to choose actions and move through the environment. But as we update the parameters, we could be using old data. We can limit the size of the replay buffer to control how far back like we actually go, because we don't want to use data that's too old necessarily. That could introduce a problem as well, because then we're making it even more off policy training, right? Because when we do the loss function, right, we're using the current parameters, right? Some of this data was collected with old parameters, although the target values were actually also using a target network, which we're updating on an older interval. So this is a version of the DQN algorithm, which it basically just takes the Q-learning algorithm and it adds the replay buffer to it. And it also adds the idea we had before of using a target network that we update more slowly to compute the target values. So we're just trying to like break correlations and try to deal with the problem. Of course, like some of the problems we encounter that we have to fix with DQN, some of them we could also fix by just doing semi-gradient sarsa instead, because that, again, is at least an on-policy method. But, you know, of course, like all these tricks, they're just like tricks that we hope work. Like there's no guarantee that doing this prevents the problems that we get with off-policy training. It's just that people really like the idea of Q-learning because, you know, Q-learning works well in the tabular case. So we try to extend it here. Now, there are lots of other extensions of Q-learning to approximation. Again, a lot of them are mentioned in the Sutton and Barto book. You know, some of them, examples use eligibility traces. We could cover these before, but there's this Watkins Q lambda algorithm. I mean, these are outside the scope of the multi-agent book, but these are other approaches that have nothing to do with DQN that are ways of trying to approximate something like Q-learning, but get it to behave better and avoid the problems we get with off-policy training. But this is one example. There's also stable algorithms. So there are some stable off-policy algorithms. Unfortunately, I believe they only work in the linear case. Yeah, example here. Yeah, they only are defined for linear approximation. But, you know, you also don't have to do off-policy learning to begin with. You can just do, yeah, stuff with, I mean, this is actually quite successful as well, this sarsa lambda that uses eligibility traces. This, even though this doesn't use like a mini batch when you train, the way this accumulates a gradient effectively also kind of does some of the smoothing. Like some of the benefits we get of training with a batch is that we kind of average some of the changes we get from a single example. And this kind of accomplishes that in a different way by accumulating sort of a gradient over time. But anyway, so yeah, this is sort of like a fairly famous algorithm. It had some success on some like Atari games. It was used, and actually there are extensions to DQN. Yeah, the other like the main difference here is that we're actually computing the loss function on a batch of data rather than a single example. Now, another thing you have to keep in mind is if you see examples, like here we'll see where this algorithm outperforms other algorithms, at least with a certain number of training steps. Every time step, this is updating the loss across a batch of data, a batch size B. This is a lot more updates than we do with normal Q-learning. Right here, we're updating the loss with a single example. Now, it's true, we get some parallelization advantage. Sometimes we can compute this loss on the batch almost as quickly as on a single example. Sometimes that's true, sometimes it's not as true. It depends on how efficient, the back propagation is. It could be written in a very efficient way for just a single example as well. Probably not. I mean, it wouldn't be efficient on a GPU, but we're actually doing a lot more computation this batch. So it's hard to tell exactly if the advantage we're getting is really because this is working much better or just because we've effectively crammed in a lot more gradient updates than we would normally have. You can see in the book, they have this example here of the deep Q-learning algorithm, how it performs on this task, this is effectively just a grid world task. They take, if people remember the level-based foraging example, this was introduced as like a prototype multi-agent problem where we have multiple agents, multiple items, and the goal is they have to move through the environment and coordinate to collect items. This has been simplified so that there's this one item, the goal is to get to the item and pick it up. It's effectively just a maze problem where the agent's just trying to find the exit, where the item is the exit. In fact, I would say it's so close to that type of problem that I don't even think it's worth formulating this as this level-based foraging. You could just do it as a maze task. But this shows the performance of deep Q-learning, how they've written it, and then DQN is shown to do much better over this many environment time steps. Now, they haven't extended this out to know, I assume they're implying a few different things here. I mean, one thing they're implying is that these algorithms never achieve the performance of DQN. The other thing they could be implying is that these just have to run longer and do have more environment steps to reach this performance. They're kind of different claims, right? One is that this converges faster. The other is that this is avoiding a convergence problem where these don't actually converge properly because of all those problems with correlation. Now, if you look at this environment, this is a really small environment. Right, there's very few states. So you could treat this as a tabular problem, solve it exactly, very easily. Now they claim here, these learning curves, they're trained for 100,000 time steps. When they use DQN, they use a batch size of 512, a buffer of 10,000, and then they update the target network every 100 time steps. What they don't mention here is what type of function approximation they are actually using. Because this problem, right, doesn't need a neural network to solve. In fact, you could apply DQN. There is a trivial version of these algorithms where they are equivalent to a tabular problem, right? Because you can make your function approximation. If you go back here, like here's an example. So here's, right, there's this parameter matrix here that's being multiplied by the feature vector. Now, if your feature vector is just a one-hot vector that includes every state separately, then your parameters will just be individual values that value the state or the state action values at each state. The gradient becomes trivial, right? It's just a version of state aggregation where you map every state individually. So you can always apply any of these algorithms to a tabular problem. It's just that the function approximator is one where everything maps, each parameter maps to a single state action value. Now, if you do that, you don't have the deadly triad problem, like you don't have any of these problems. So then if they're using that kind of tabular approximation here, it makes sense that DQN would converge faster but that's just because it's doing way more computation, right, on each step, right? It's not because it's actually performing better. Now, if you're using a neural network and you have all these other issues with correlations, then it may be that DQN is actually solving some of those problems. Now, I actually was starting to implement some of this. Basically, oh yeah,
Oh,
Frank, yes.
sorry, Jason. Quick question. So is a batch that's done in DQN similar to the difference between like a stochastic gradient descent versus a mini batch gradient descent? Kind of
Yeah,
like,
like true stochastic gradient descent, right? You would take one example at a time. And
right.
then
So
batch
I was
gradient descent,
wondering,
you
is
do a
that similar?
batch. Yeah, it's the same thing.
Okay. And then for the dual network one, is that just similar to saying, hey, my feedback is going to be slower because otherwise I'm always updating myself on the same steps. So in some sense, it's a little bit more stable in the feedback.
Yeah, it's stable with the um like you already have the problem of seeing too many examples that are correlated closely together in the state
Yeah.
space. And then
Yeah.
that's already going to be a problem with the gradient. If it's also a problem with the target value, right, it could also contribute to the divergence problem which
Okay.
happens with bootstrapping. So yeah, this sort of breaks the bootstrapping a little bit. It's still bootstrap going back like 100 steps in the past, but
Mm.
it works your way closer to having the target values be constant, like not depending on the parameters, which
So
is
just
what,
making,
yeah, I mean, we would like ideally to make it a true gradient method instead of a semi-gradient method. Right? We don't want the target values to depend on the parameters. And
just making
this,
sure. Oh, sorry.
oh yeah, go ahead.
No. So are there two updates for theta, theta
So
dash and
theta
theta?
bar will
Theta
be
bar. Yeah.
updated. It will just be reset to the current theta on some interval.
Ah, okay.
So
So it's a slower, right? Slower update.
yeah, so basically there's a time when your target values will be based on a network from the past.
Yeah. Gotcha. Okay.
Yeah, so like let's say we updated the target value that might have helped a lot for one state, but it screwed up the value estimate for a different state. Then we see that state. If we're using an older target network, maybe we have the benefit of not, you know,
Yep.
necessarily
Correlated.
screwing up that
Yep.
value.
Thanks.
But right, I mean, these are just attempts to fix the problem, right? They don't necessarily. So now this is a very simple task. Um, I mean, right, this should be one. And like ideally, this, I guess the maximum reward here is one. So I was just working on implementing this, or adding like a DQN implementation to the code I already have, for ordinary reinforcement learning. Um, there were a few things. So actually, the way I did the replay buffer is that when I visit states, right, I'm always like, one of the properties of all these approximation algorithms is that you need to, right, map the state to a feature vector, because then the feature vector is what is used in the function input, whether it's a neural network or linear function, whatever. So here, like, I'm always, as part of these algorithms, I'm always like taking the state and updating the feature vector. Here in the replay buffer, I'm actually just saving the feature vectors rather than the states, because I'm going to have to use them anyway to compute the gradient. I don't want to have to recompute the feature vectors every time I select a new mini batch. So, it may, the memory, might be an issue if you don't have enough memory to store, depending on how big the replay buffer is. But that is one of the things I'm doing. Yeah, the target update. Oh, okay, fine. So you do DQN. Now, I set up this tabular grid world problem. It's actually the same exact grid world that I have in here. Where value iteration. Sorry, okay. So I have this grid world. Sorry, I reuse this example a bunch of times. I'm just trying to find the place where I am using it. Deterministic. I thought it was just here. Okay. Well, anyway, it looks something like this, but you have a starting state, a goal state, right? And there's wind, which like will blow you up in a different direction if you're trying to move. It just makes it a little less trivial, so you have to kind of loop around to reach the goal. The point is, this is a simple tabular problem, kind of like the grid world in the book with the foraging example. So we can get an exact solution here. This is just like an example of what the value function would look like in the policy. But anyway, here I'm using a version of the grid world. I've constructed it here. And then value iteration is an exact solution technique. We have a tabular problem, and we end up with, a value function. Again, they're all just, individual values, and an optimal policy. So this happens, I get statistics on how this performs. So it finds the goal in a mean number of steps about 20, and there's some variance around it because this is a stochastic environment, right? But it is tabular. Now I can do normal Q-learning on it. Sorry, this is an approximation technique, right? Like this version of Q-learning has parameters, right? There's this parameter matrix. Here I'm using linear approximation. However, because this problem is so simple, the type of approximation I'm doing is just effectively the same. Like notice this is my parameter matrix. It's 70 by 4 because the state vector has 70 elements. It's a length 70, and there's 4 actions, 1 for each direction. Now, this matches, if we look at the value iteration solution, there's 70 values, right? There's 70 states. There's a distinct value for every state. So here, my parameters that I'm learning are actually distinct for every state. So it's a trivial version of function approximation, which doesn't, right? I'm just mapping each. So actually, these individual values are distinct from each other. When I update one parameter, it doesn't affect the state values anywhere else. I said, like, you can always take an approximation technique and apply it to a tabular problem because there is a trivial version of function approximation that, works as a tabular problem where we have these, 70 by 4 parameters. So here what I'm showing is the performance of this over time with regular Q-learning, or this in the book, this would be like the equivalent to DQN. And we can see that this is like showing different learning rates. It's doing over time. I have a very low value of epsilon, so this isn't being punished too much by the random actions. We can see the learning rate doesn't make too much of a difference. I'm running this over 20,000 steps, and it sort of started to flatten out already. But this is reaching a performance of like about, this is showing the average reward per step. So this is like about 37 steps. It's a little noisy. It's hard to tell. I mean, it could be a little better. If this is 0.03, it's about 33 steps. The perfect solution, right, is like 20 steps. We can see it's not, it hasn't found the perfect solution, but it's still pretty successful. So now we can compare this to DQN. And here I'm running DQN, the same kind of thing. Over different buffer sizes, I'm using the same parameters as was shown in the book with a batch size of 512. 100 is the update interval for the target network. The learning rate, actually, in this case, doesn't affect it that much. So here, I actually found, at least with this example, that using a smaller buffer size helped a lot, right? If the buffer size is 10,000, that means that one of the samples being drawn for the batch update could have been 10,000 steps in the past, where the behavior of the network was pretty different. They don't actually show in the book differences in buffer size. But here, this did achieve, so here, these sort of plateaued a little earlier, I would say, right? Than this, it's over the same number of steps. So it is converging faster. This actually overall converged to a better result total. But in this case, because we don't have any of the problems we usually get from correlated states, because I'm not using a neural network here to approximate. The only reason why this is converging faster, you can see it takes way longer to run DQN than just the Q-learning, right? This only took like a few, like 700 milliseconds, and this is like, 29 seconds. So it's quite a bit longer, because when we form these batches, right, we're doing this whole batch update every step. It's way more expensive. I mean, the other thing with DQN is that, there's way more parameters to worry about. So like if we go back to the book, right, when we do DQN, like we need to have a buffer size. We need to have a batch size. We need to have an interval on the target network. And then there are more things that can be introduced, because as the book mentions, there are extensions to DQN that were thought of later. There's an idea of actually using the target network even differently by also selecting the argmax. Like this is the double Q-learning idea. Selecting the argmax from theta, but then using the value from theta bar. And then the other, double deep Q networks. Another idea, there were multiple ideas put together in rainbow DQN. Now, this was an algorithm that just added a few more features to DQN. There was a recent post and paper someone made of sort of revisiting rainbow DQN, because they talk about all the different elements that were added. So this is sort of a summary of different elements that were added. So one is the double learning. That's like using the target and value network, combining them to get the target value. This is probably maybe one of the most important ideas, is the prioritized experience replay. So this is not just sampling from the replay buffer, but looking at the replay buffer and trying to estimate which states in the replay buffer are most informative. We'll provide, the best update based on the current network. Multi-step learning. This is, again, in Sutton and Barto, they talk about eligibility traces, which is one way to incorporate multi-step learning. You can also do just n-step learning, where actually with a replay buffer, it's pretty easy to do multi-step learning, because you already have the data set where you can see multiple steps in the future. But this is just, instead of just using the target value, like the bootstrap value, you add up rewards for a certain number of steps. This is another way to help break correlations, because actually using, another way to break the problem of the network being overfit to states in a certain area, because you actually use the real reward values for some of the states instead of just immediately using a bootstrap value. This is a little complicated. It's not really mentioned in the book. There's also another idea of replacing epsilon greedy exploration with introducing noise in the neural network itself and using that to explore. And then over time, the network will start out very noisy and random, and over time, the network will learn to adapt to the noise and fit better. So they show here some examples of removing elements from DQN and showing which matter the most. It appears like the single, so this red is showing DQN, and then one of the higher lines is rainbow. But it looks like removing any one element doesn't seem to be too much of a problem. Perhaps it also depends on the example problem here. This is showing when you add individual elements to DQN, which give you the best immediate improvement. It seems like, and the top one here in most cases is rainbow. It seems like the distributional, what's purple? Yeah, the prioritized experience replay probably is one of the most important additions here. It's actually not too different than what I saw here, where if you shrink the size of the replay buffer, you can get better performance, because this effectively, eliminates older examples that you don't want to use from the replay buffer. There's different ways of making the replay buffer more useful. Shrinking it is one. The prioritized experience replay is another. But, there's just a bunch of little tricks added. And you could see I've only incorporated a few of these elements. I could easily, maybe in a couple weeks, I'll have time to add some of the more ideas to DQN to make it more closer to the rainbow algorithm. But I think, if you look at this, the more of these things you add, like, it's true, you can get really good performance, and like DeepMind showed really good performance on Atari games with Rainbow. The problem is that there's a lot of hyperparameters. Like, as you add all this, you're just adding more and more hyperparameters to this problem. Like, if you do prioritized experience replay, that introduces, well, I guess it's not mentioned here, but exactly how you do it has its own hyperparameters. And sometimes all the hyperparameters are just really hard to tune, and you may have to tune it over a bunch of different trial runs. And at that point, the fact that it converges faster might not matter, because you have to waste all this time, figuring out how the hyperparameters work. So, sometimes if you use like a much simpler algorithm like this, semi-gradient sarsa, which we saw, this is similar to the deep Q-learning, so when you introduce eligibility traces, this is another way to mitigate some of the problems and to add n-step learning to your algorithm with, like this sarsa lambda algorithm implemented here. And this only has one additional parameter, which is this value of lambda. And this hyperparameter is not really that arbitrary. It's something that when you evaluate returns over different values of lambda, you can usually see very clearly what the trend is and which value of lambda. And you can also kind of improve it throughout the training process. You can cycle it throughout training and change it. This is way more straightforward than messing with the, what we do with DQN, where we have to actually mess with the buffer size and the target update. I mean, these are things that could affect performance in weird ways that aren't as straightforward to track. Like, if you're trying to do hyperparameter tuning, it's nice when you're just dealing with simple hyperparameters, like the learning rate is a hyperparameter, which usually you can tune well because you can see some sort of, convex behavior of the convergence according to the learning rate. But some of these other hyperparameters are really hard to figure out. And when you do rainbow, something like rainbow DQN, you add more complexity to that. So again, like in the Sutton and Barto book, there are other approaches to value function learning. The other major class of approximation algorithms, which they have some advantages, are policy gradient algorithms. And this is something, again, if you go back to these earlier videos, in this video talking about approximation methods, in the second one, which is the last video in this playlist, I talk about policy gradient methods and how the advantages they can have over value function methods, and why we might need policy gradient methods when we use approximation functions. So I think the goal of introducing policy gradient algorithms is because we're going to probably need them to do multi-agent problems, but also there are a whole class, kind of like the DQN and rainbow DQN. There are all these extensions. Like, this is the simplest type of policy gradient algorithm, reinforce. We'll maybe talk about it more next time. But the remainder of the chapter looks at all these extensions to normal policy gradient algorithms, including PPO and also concurrent algorithms, where we have parallel environments and we try to combine it. Sometimes these policy gradient algorithms actually have a lot fewer hyperparameters you have to worry about than something like rainbow DQN. So I think we'll save the whole discussion of policy gradient for next time, and I'll try to implement some stuff with parallel, like synchronous environments, because there are some pretty simple things you can do to just vanilla policy gradient where you just combine data from multiple environments, vectorize it, and you can get a very quick speed up in performance, which has nothing to do with a replay buffer and sampling old things from a replay buffer. This type of parallel vectorization of data, I think, usually ends up working way better, because even if you have a replay buffer, you still have the off policy training problem, where you have this old data and you're trying to figure out which of the old data is most useful, and or you want to shrink the buffer. So for next time, we should hopefully just conclude the discussion of policy gradient, parallel environments, and then, yeah, summarize everything. And this will sort of lay the foundation for the first ideas in multi-agent deep reinforcement learning. Of course, we're going to start with value function methods, just like we do with normal reinforcement learning, and then move on to policy gradient methods. And eventually, although not until like the very end, we'll actually get back to some of the game theory stuff. But as we saw with even the tabular problems with estimation methods, a lot of the multi-agent approaches you start with, and sometimes all you actually get to, are just sort of single agent reduction, like things that effectively reduce the problem to a single agent problem, where you're not actually looking at anything that makes the multi-agent problem special. And sometimes that's just because it's not even possible and you can't, calculate like a game theory solution. But we'll see. There are some examples of algorithms that try to do that. We'll get to it eventually. But for next time, we'll just look at the extensions, sort of fancier, more modern extensions to policy gradient algorithms. So before we wrap up, are there any questions about anything we did so far, or any of the links, the resources to that where we covered this stuff in the past? Okay, well, if not, thanks for coming, everyone, and yeah, we'll wrap up for now and hopefully see everyone next time.
Thank you.